In this video, we're going to talk about a special type of integral called an improper integral. And improper integrals come in two main types. And in this video, we're going to talk about type number 1. Type number 1 of an improper integral has the property that either the upper limit of integration is infinity, or the lower limit of integration is negative infinity. So an integral of this nature is asking the following of you. Suppose that you had a function that looked a little bit like this one, decreasing smoothly toward the x-axis and has y equals 0 as a horizontal asymptote. The question is, if you added up all the area under the function from now to infinity, would you necessarily get an infinite area under the curve? Or is it possible that you can add up an area over an infinite width and get a finite result? As it turns out, it is possible to add up an infinite collection of things and get a finite outcome. And there's actually a very simple instance of adding up an infinite collection of things and getting a finite result. And that can be demonstrated simply using a square. The area of this square is 1. So no matter what, if you add up quantities that all fit nicely into the square, the result will be smaller than 1. So for example, if I add up 1/2 to 1/4, 2 1/8, to 1/16, to 1/32, to 1/64, and so on, if I add up 1/2, 1/4, plus 1/8, plus 1/16, ad infinitum, as many of these as you want, continuing this general pattern, the result of that cannot exceed 1. So it's very, very possible to add up an infinite collection of numbers and get a finite result. And the question is, can you add up an infinite amount of area and get a finite result as adding up all of that area? Now, to actually calculate an improper integral, here is the usual technique. Integrate, for example, from 1 to infinity, 1 over x squared. Find, if possible, the total area underneath the curve 1 over x squared as x goes from 1 all the way out to the horizon. Now we're going to begin this in the same way that we would begin any definite integral. We would begin this by finding our favorite antiderivative using the power rule. But it's inappropriate for us to quote-unquote plug in infinity, because infinity is not a number and cannot be plugged in. Instead, we're going to plug in something that we will call b as a placeholder, and then we will let b grow very large. In the language of limits, we will let b approach infinity. So, if I plug in b and if I plug in 1, and then I take the difference between these two quantities, plugging in b will give me -1 over b, or b to the power -1, and then subtract -1 over 1. After simplification, this would be 1 take away 1 over b. Now, b was just a placeholder, and if we let b approach infinity, then 1 over b will shrink towards 0. So this limit will work out to be 1, because 1 over b is going to completely go away. So imagine this. Here is something that looks very much like the graph of the function 1 over x squared. We found the area under the graph as x goes from 1 to infinity. And not only was that area finite, that area was extremely small. That full area from x equals 1 to x equals infinity was equal to 1 square unit. That's unbelievable to me. And that's the magic of improper integrals, being able to add up an infinite quantity and get a finite result. This is going to be one of the major themes of Calculus 3, should you decide to take that course, adding up an infinite collection and getting a finite result. So in the next video, what we'll talk about is the second type of improper integral, in the case that not necessarily is one of your limits of integration infinite, but maybe one of your limits of integration is an asymptote of the function.